Good morning, everybody. I'm Chou Thao. This is my design for MIPS ISA. This is for Class C CS 440, clear architecture. Let's begin. Today in the overview, we'll go over the processor, basically the basic details. We'll go over instruction types and formats, and again, different addressing modes that support it. The architectural design, we'll go through layers, every detail.
Good.
We'll talk about implementations, Verilog, and then we'll talk about enhancements that we did implement and feature enhancement. Some, not all.
You gonna tell us what zinc stands for?
Oh, zinc. Well, let's go back to that. Zinc, well, there's this arm wrestler that I really like. His last name is Berzik. So I just took out the bird just in case, don't want any losses. So just took the zinc because it had a
Okay.
catchy tune to it.
There's always a backstory to all that stuff.
So the processor, we have a 32-bit MIPS ISA architecture. The memory is handled over memory architecture. It's big even. Therefore, the most significant byte is stored in the lowest byte of memory address, and the least significant is stored in the upper. It's separate instruction and data memory, so they have separate pathways. There's 32 registers. 3 specific ones is register 31, which is your return address, register 29, which is your stack pointer, and the 0 register, which is always 0, constant 0. The data types we have so far, for now, we're supporting only 2. It's 32-bit unsigned and 32-bit signed integers. Our flags, we have a carry, a negative, overflow, and a 0 flag. We do have an interrupt enable flag as well. I forgot. My fault on that. So our instruction types and format. So R type is allocated for operations dealing with multiple registers. In this case, we do have a destination register. In later cases, we won't have a destination in a sense with this. Yeah. So our opcode for register, how we know it's a R type is that the upper 6 bits of the instruction is always 0. Then in here, the function, which is the 5 least significant bits, the 6 least significant bits are allocated to our different function operations, so arithmetic and logical. We have a shift amount, that's for our barrel shifter, which we'll get into detail later on. We have 3 registers, a source, a temp, and a destination. These 2 will be operands, and this will be a destination. Moving on to the next one is I-type, immediate. Immediate, in which case we allocate the shift amount in the function is now removed, as well as the register destination. So the last 16 bits is allocated to a 16-bit immediate. We still have a temp and a register source. Opcode will dictate which type of operation or which type of immediate operation is to be performed. The other type is a J type, which are allocated for jumps in this case. But in this time, we don't have any registers at all. It's a 26-bit immediate, and the upper 6 will be allocated to the different type of jump. Addressing modes, we have immediate, index, register, direct, and PC relative. Let's get into those. Immediate. Let's get into the first one, immediate. This is used in almost all I-type instructions. And the operand corresponds to the lower 16-bit of an instruction like this instruction, for example. So it's always, the operand is encoded in the last 16 bits of the instruction. Index. Content, so this is the contents of the register. This is usually used, it's constant of a register plus a 16-bit immediate. This is always used for a load and store to get effective address, in which you access memory itself, data memory, in this case for a load and store. Though we'll get into another one for I/O memory. So we have a register, which is, this is supposed to point to the 4. This one here, that's my fault on my end. And the register is allocated to the 7, the 4 is the immediate, so it'll be that way. And then now we're looking at register indirect. Register indirect. So the operation is embedded inside a register. This is, yeah, these are in every R type instruction. So in this case, we're just looking back at a store word, for example. It's the contents of that register will be the operand that will be used for calculations and the affect the address.
Where do we get the 7 from? I'm not that
Seven
clear.
is from the source.
Well, that's not a 7 though. I mean, you've got a value of like 12 or something.
Yeah, that's a mistake.
Okay.
So, okay. Let's get into direct. We have a 32-bit. So direct is full on 32 word. But then if we do that, then we don't have any support to decode what type of operation we're performing. So therefore, we support a pseudo direct in which we use 26 immediate. And this is in the case usually used for jumps and jump lengths. Therefore, it's 26. So upper 4 bits of a PC will be encoded into your next location, and then 26-bit immediate is encoded in the next, and then the lower 2 bytes will be 2 zeros. It's missing there.
Yeah. What's the 0, 1?
So it'll be a 0.
And then you only have looks like 18 bits inside the box.
1, 2, 3, 4, 18.
Yeah, it's not 26, right? So we're missing a little bit
Yeah.
of data there. Okay.
Missing one more data.
Yeah.
PC relative. This is using a 16-bit immediate offset. These are for branches. You add that offset to your current PC counter or your program counter. If a branch is successful, in this case, if our current PC is 8, we'll add these 2 together. Yeah. Our new PC. Now let's get into the underlying architecture. We have a central processing unit, which has a control unit and an execution unit. Then it interfaces with a I/O memory and data memory. This is our diagram. This is our CPU. This is data memory. This is I/O memory. We'll get to the details later. Data memory has, for our purposes and this for test cases, we only use 1 by 32-bit decimal space, which case this can hold up to 4 gigabytes. And this is where it holds data you can read and write into this memory. Here, I forgot, go back. We'll get into this later because this is an enhancement to our MIPS architecture, so I will go over this detail later in the slides.
Good.
This is our CPU. So inside the CPU, embedded inside the CPU is a control unit and an execution unit. So a control unit is a finite state machine. This fetches, decodes, and it sends out, it communicates between our execution unit and memory, as we show outside data memory, I/O memory. It has various control words, which is for PCs, for memory, functions, addresses. So it's different mux control words, interrupts. This is our execution unit. Our execution unit has an instruction unit and your data path. These 2 communicate between each other all inside the execution unit. This is an instruction unit. We have the PC, our program counter is kept locally in here, as well as the instruction memory. And here we have a way in which we output our instructions. So other modules can interact with instructions. Instruction unit holds a PC pointer and the instruction register. So PC mux We have PCN, this is data that's coming in. We have, this is for our jump, where we have the upper 4 bits allocated to a previous PC, and then we have the middle and the next 26 bits will be from our instruction, as well as candy with 2 zeros at the end. This, on the other hand, is used for branches. So our branches are PC plus our sign extended 16-bit immediate offset and 2 zeros.
What's PCN? Where's that come from?
PCN, this is coming from our integer data path. This is basically sending a data, so it's usually used for our jump register.
Oh, jump register,
Yeah,
got
so
it.
we're able to get the data and then can change the
Okay, got it.
PC into whatever is inside your register.
Good.
This is our instruction unit. This is the memory. As again, it's 1K by 32 addressable space. This is for testing purposes. It holds your instruction. This is only readable. This is not writable into. You have data that comes in and out of it. This basically holds your instructions.
But you just said it's not writable. So
It's not writable, it's readable.
But what's data in for then?
Oh, that's because I use a template for a memory module, and it had a data in, and I forgot to
Okay,
run
okay.
that. Yes. This here is our integer data path. It has a register file, which is 32 by 32 registers. We have our AU, which performs our various operation, logical, and arithmetic. We have our 2 special registers, high and low, that's for multiplication and division. We have AU out, which is basically the output of your AU from your calculations and operations. We have our data in. This particular register has 2 data inputs. One that comes from I/O memory, and then another one that comes from data memory. And that'll be, and whichever one is needed for the current operation will be through a dy select. So you can't really see that, but it's dy select there. Our integer data path, we have a demux. This is for your data. So if you wish to write back into data memory itself, we have various communication. We allow register 29, which is stack pointer, register 31, which is return address. We allow a T address, this is for immediate. And then we allow a D address, which is for ALU regular operations for our registers. And then our TMUX. This basically allows us to store our load. So if we're bringing data in from, oh, no, sorry about that, let me backtrack. Okay, this TMUX, this allows 16-bit immediate. So this allows our 16-bit immediate operations. So we have a 16-bit immediate, or we could take data from a register. And you have control board, it's a T-select, which will you pick which of the 2 choices, depending on the operation. Introduce. So this is the YMUX. This is what we wish to output, depending on the operation. So we select a design. So DY this is data memory. So this is the input that comes from data memory. And then DYIO, that's IO memory. Okay, so that's usually used for if you wish to load or say input from IO memory. So that allows us to write into our data, which if you output in the previous slide, it allows us to. So if we look at here, the output from the YMUX goes back into D. So that allows us to write back into the register file. This PCN, it's not registered, I forgot to put it outside, but it's outside the input that comes in from PC. So our MUX is actually much bigger than the one that's shown. And that allows us to do a jumping link. So it allows us to store, basically bring in the data from PC, and then that allows us to store into a register, particularly a stack pointer or the return address. Let's take a look at our AOU. We have 4 various modules. We have MIPS 32. This performs every operation except for our shifts, multiply and divide.
Good.
These two allocates for, the multiply is specific for multiplication, which will produce a 64-bit product. And the upper 32 bits is stored in Y high, and the lower 64-bit is stored in Y low. Same with division, however, it's the product, no, it's the quotient and the remainder. The remainder will be stored in Y high, and the quotient will be stored in Y low. In our barrel shifter, we have various operations for shifts. For this case, we were time constraint, so I only implemented 3.
But those are the three. Those are the three that MIPS does.
And this allows us to shift a certain amount, therefore you don't have to keep looping if you're only shifting one at a time. Let's get into the detail. So our ALU performs the various arithmetic and logical operations for our processor. Most operations are contained inside the MIPS32. Multiplication and division, that's inside our mult32 and divide32, and we are shifting through a barrel shifter. This is our barrel shifter. So this is the implementation of our barrel shifter. We have a function. This is a 5-bit opcode. I wouldn't say, but I was a little too lazy to shorten it because we only have 3 shifts currently. But then this does allow for feature expand. We have a shift amount. So we have data that comes in and data comes out. This is used, so if you go back to our barrel shifter, you can see that, let's see, T, whatever data comes in through T will be our input. Barrel shifter uses only the 32 bits from T register. So for the first part, this is a this is a logical shift left. So we shift the data by shift amount to the left. And same can be said about a logical shift right. We did the same, but now we shift the shift amount to the right.
Mm-hmm.
This here is the nitty gritty. This is a shift arithmetic right. The issue with this is that the most significant bit, whenever you shift, you drop. So if you're shifting right, you're dropping, or you're discarding whatever bits that shifted right to the right. But what you do instead is you copy the most significant bit, and you replace all the missing bits in the upper, now that you shift everything to the right, with the most significant bit that was previously there. So this is all the copy operations. This allows you to shift. And that goes into our data that comes out. Barrel shifter flags, it only handles 0 flags, which check if the output was 0. Negative, which checks if the very first bit is a 1, indicating that it's a negative. And then determines if there was a carry flag. This is specific for, this top one is specific for our shift arithmetic rate. This checks if this checks for overflow and carry. So if something shift out, it will go to the carry flag. And checks if it was a 1 or a 0. And this is if the case that if it's just a logical shift, then it just drops.
What function code is 0E that you're checking there? So you say,
That is an arithmetic shift right.
but can we ever overflow if it's going to the right? No, I don't think so. Because
No?
you're dividing making the numbers.
But then it goes to the carry flag.
You can't overflow a
Yeah.
number if you're dividing it.
Oh, that's,
So in essence, you're dividing by 2 every time you shift.
okay.
It would never overflow.
Okay, I see.
Yeah.
Okay, so that will be
Have to
Fixed.
change that, yeah.
in a feature enhancement. So enhancements, we have reverse enhancement, IO memory. Instruction, we have a halt, which stops. We have return for interrupt, sets, and set the interrupt, enable flag. Our IO memory, as well as for testing purposes, 1K by 32 byte addressable. Interrupt handling, it handles through handshaking, so it's, in my case, I use it outputs an interrupt request and receives an input input from control unit, interrupt acknowledge. And it starts the request once the instruction set interrupt enable turns on, so the interrupt enable flag inside the control unit. It's set, therefore it sets out a request, receives an interrupt. And the input output is similar to a load and store. Input is like a load for IO memory, and output is the same as a store for IO memory. So you're able to read and write to IO memory. Future enhancement, we would like to add a floating point unit. This will allow more precise calculations, decimal points. A vector unit, this will allow multiple operation and multiple data. This is very similar to the concept of pipeline. You'll free CPU time by calculating multiple data at any given time. And we will enhance our IO interface, therefore having a control type of interface, allowing various peripherals to interact with our IO memory. And last but not least, we'll add more instructions. And that's it.
All right, very good, thank you.